Hello everybody and welcome to Climate Change Day 17. Last time we were together we learned how scientists have used ice cores to determine the Earth's climate over the last 700,000 years. Unfortunately, the ice is not infinitely deep, and so if we want to understand what happened farther back in time than that, we need to look into the geological record. Come along. Our quote for today comes from the president of Ethiopia, Sahle Work-Zewde, who says, "Winning the race against climate change is about building prosperity and well-being for everyone." By the end of today, you will be able to explain the prehistoric climate conditions on Earth and how we were able to determine those. The Earth is 4.6 billion years old, and of course, that's a really long period of time, and so we will not be able to cover all of that in great detail in this class. But today, I'm just going to give you a little bit of a primer on some of the key events that occurred there. Our ice cores only take us back so far. Glaciers are only so deep, and as we're going to see, there have not always been glaciers present. If we want to go back farther than 700,000 or 800,000 years, we have to look to geology for answers. So over here on the right side of your screen, you'll see a little graphic which shows the history of Earth broken up into eons, eras, and periods. And the scale is in millions of years ago. So here's today, and if we go back 65 million years, we get to the boundary between the Tertiary and the Cretaceous period. And we go back farther, we can get to the end of the Mesozoic and get into the Paleozoic era. Our ice core data only goes back about 700,000 or 800,000 years. And so that doesn't even go one number on this axis right here. It only takes us half of the way back through the Quaternary. In order to determine what happened back here, we're looking at rocks. Whereas determining the climate from ice cores is straightforward, determining the climate from previous eras and eons using geology is a little bit more involved. We end up combining multiple methods to put together as complete a picture as possible. In order to put that picture together, we have to use what we call paleothermometers. And these, just like ice cores, determine temperature based off of isotope ratios. And this paleothermometer, which comes from the oxygen-18 concentration in Foraminifera, which are these really small sea creatures. They're a protozoan. They live on and in the sea floor. Well, these guys, they produce shells made out of calcium carbonate. And when they die, that calcium carbonate is left behind with whatever atoms were present in them at the time. And so in that calcium carbonate, you've got oxygens, and those oxygens can be oxygen 16s or oxygen 18s. And the ratio of oxygen 16 to oxygen 18 in that carbonate can be used to determine temperature. If we look at the concentration of oxygen 18 in deposits on the seafloor, and we compare that to the deuterium concentrations in our ice cores, in this case looking at Dome C, we can see that they line up with each other. When we have high levels of deuterium in the ice, we have low levels of oxygen 18 in the sediment. And here it looks like it's high, but we've just inverted the axes so that way it lines up. And of course, they're going to be inverted because if you have extra oxygen 18 in ice, you will have less of it in the land because it's the same oxygen, it's just in different places. And because our ice only goes so deep, our record in the ice only goes back 800,000 years. However, we can go much, much farther back with those sediments on the sea floor. The colder it is, the larger the ice caps. And when there's larger ice caps, less oxygen 16 remains in the seawater, and therefore a higher concentration of oxygen 18 is available for incorporation into foraminifera shells. When the foraminifera die, their shells build up and form limestone. That signature of the isotope ratio of oxygen 16 to 18 that we can use to determine the temperature is trapped in that limestone forever. we can take those numbers back to 2.8 million years ago. And we number them, all of the increases and decreases in warm and cold cycles, and we call them marine isotope stages because these are isotope ratios found in marine sediment. And we number them 1 from the present day back to MIS 104 2.8 million years ago. Times with high oxygen 18 concentration in limestone, and therefore higher concentrations in seawater, have even numbers and represent cold glacial intervals. And times with low oxygen 18 in limestone and sea odd numbers and represent the warm interglacial periods. So you can actually go through and you can count the warm and cold values. We are currently living in a warm interglacial period. And so you can see that even over the entirety of this record, and this graph is actually only showing the last 800,000 years, that there has not been a time where we have experienced warmer conditions than we have now. Foraminifera is only one of many paleothermometers that we put together to create our picture of Earth's past climate. Another one is looking at the calcium to magnesium ratio in calcite, which is limestone, because it turns out that while limestone is primarily CaCO3, if you have higher temperatures, you start to incorporate small amounts of magnesium into that compound. And so therefore, the higher the amount of magnesium that's present in your limestone, the higher the temperatures were where it formed. If we only want to look within the Holocene, we could actually investigate the calcium-strontium ratios within aragonite, which is a coral skeleton. And this is really cool because we can actually see as the corals grow the different layers, and so we can actually get subannular resolutions of temperature, and so we can see how much warmer and colder it is at different times of the year. And this works because strontium occurs as a trace mineral in coral skeletons at very low ratios, but that ratios do change with higher temperatures. So when the water is warmer, more strontium gets included. If we want to look back over longer periods of time, we can look at Tex 86, which looks at the structure of rings in an archaea, which is a prokaryotic cell that is temperature dependent. And if we want to go back to long periods of time, so we want to go back to the beginning kinds of multicellular life, we can look at clumped isotopes. And in this, we're looking at bonds between carbon-13 and oxygen-18 in carbonates. These heavier isotopes, so carbon-13 being heavier than carbon-12, which is the predominant species of carbon, and oxygen-18, which is heavier than oxygen-16, our predominant species of oxygen, form bonds together at higher rates than you would expect to happen by chance. And the cooler the temperature, the more frequently it happens. So if you look at the frequency that you would expect carbon-13 and oxygen-18 bonds to form, and then you look at the frequency that they actually do, you can determine the temperature when they formed. If we put all these together, we can paint a picture of our paleoclimate. Earth's climate has been more extreme in both directions than it is today. There have been times when we have been in hothouse Earth, where there have been no glaciers present, not even at the poles, and there have been times, like now, where we are in icehouse Earth, where we have ice sheets present at least one of the poles. If we want to look at climate change over a long period of time, we can look at the Phanerozoic era, which goes from a little over 500 million years ago with the Cambrian explosion all the way through to the present. And we can see the changes in temperature over that time brought to us by our paleothermometer. And the first thing I want you to think about when you look at this figure is that the scaling on the x-axis is not consistent throughout the figure. And so over here on the right side, we're only looking at thousands of years ago, and here we're looking at millions. And so in the amount of space that we're showing 20,000 years over here, we're showing 400 million on the left side. But we can see there have been times where it's much warmer. In fact, at the beginning of the Cambrian explosion, it was about 14 degrees warmer than it is now. And there have been times when it was colder, like it was 20,000 years ago. And you can see that there's been a general trend down with these rises and falls, rises and falls, rises and falls. And we have entered a fairly stable period of time over the last 10,000 years. But that stability is at the upper end of temperature that we have experienced on Earth for the last 2.5 million years. I put together this slide for you to show you kind of some highlights in Earth's history. And the first highlight that I want to introduce you to is called Snowball Earth. So there have been a couple of times in Earth's history where most or all of the Earth became encased in ice. And those, as you can imagine, have had pretty dramatic consequences for life. The next big event that I want you to be introduced to is the Great Oxygenation Event. So when this occurred about 2.5 billion years ago, this is when we have cyanobacteria evolve in photosynthesis creating molecular oxygen. When this happened, the atmosphere changed dramatically, and instead of being a reducing environment, it became oxidizing and the planet rusted. This is significant because when this shift happened, life nearly ended. If we zoom in just on the Phanerozoic eon, so where we kind of have think about most of our life from the Cambrian explosion onward, there's a couple of events that I want to point out for you. We've got the Ordovician and Silurian extinction, and this is a mass extinction that was caused by climate change. We've got the late Devonian extinction, and this was caused because new land plants evolved. We have this colonization of the land by plants, and they sequestered carbon out of the atmosphere, causing a rapid decrease in temperature, which led to the mass extinction. And then 250 million years ago, leading us into the Mesozoic era, we've got the Great Dying, which was the greatest mass extinction of eukaryotic life that we've experienced on Earth, and it was caused by increased temperatures in carbon dioxide, as well as hypoxia that was associated with that. Of all of our mass extinction events, the one that you're probably most familiar with is the KT event, or Cretaceous Tertiary event, or Cretaceous Paleogene event. And this is what killed the dinosaurs. And this was an asteroid impact that killed all tetrapods larger than 55 pounds, except the crocodilians and leatherback sea turtles. I point this one out specifically because this is the only one of our mass extinctions that is not pointed directly at a red X. So what are those red X's? Well, those red X's are the places in Earth's history where we have switched between icehouse and hothouse Earth. And what does this mean? Well, it means that at least since the evolution of multicellular life, the transition between icehouse Earth and hothouse Earth is usually associated with mass extinction. So that little primer on the geologic history of Earth is designed to give you an understanding of how we know what Earth's climate was like farther back in time than ice cores allow us to look. I really want you to focus in on the transitions between Earth as an icehouse and Earth as a hothouse, as that is when we tend to see mass extinction events, which are important to us. I hope you learned a lot today, and I look forward to discussing this with you in class tomorrow. Bye-bye, everyone.